We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
3, 2, 1, 0. All engine running. Liftoff. We have a liftoff.
0 and liftoff of the Delta rocket with Opportunity.
Rocket carrying the Mars Polar Lander.
Mars Mobile Surveyor.
Carrying NASA on an odyssey back to Mars.
Its journey back to the Red Planet.
A chance to explore and unlock the secrets of our neighboring planet.
For thousands of years, Mars has captivated the human imagination. Our desire to learn about and even touch Martian soil has spurred over 40 attempts to reach the Red Planet. Most have failed.
On November 5th, 1964, Mariner 3 was launched, but a failure in the protective shroud aborted the mission.
Undaunted, though, a new team is set to take on this epic challenge.
Let's pick a target on the feature.
The risk is great, the reward's greater. Rising from the ashes of previous failures is the Phoenix Mars mission. On November the 28th, 1964, just days after Mariner 3 was lost, Mariner 4 blasted off from Cape Canaveral with the goal of discovering evidence of life on Mars, the driving force behind almost all Mars missions. For 7 anxious months, Mission Control guided the craft on its epic 500 million kilometer journey. Loaded with an array of science instruments and a TV camera, it was designed to capture the first deep space images of another planet.
The spacecraft is flying toward Mars, about to pass within 6,000 miles of its surface.
With a comparable land mass, day length, and even seasons, Mars resembles Earth more than any other planet in our solar system. The Mariner scientists hoped the mission would find a thriving ecosystem, but the images were bleak.
Picture number 11 shows craters 3 to 75 miles across. The picture suggests that Mars has never had an ocean or substantial atmosphere. The Mariner 4 pictures neither demonstrate nor preclude the possible existence of life on Mars.
Even then, scientists knew there wouldn't be life without water, or its frozen version, ice. Almost half a century later, NASA is still trying to prove its existence on the Red Planet, and all hopes now rest with the Phoenix Mars mission. Phoenix is being led by a veteran of previous Mars mission successes and failures, Peter Smith.
First goal is to land safely on Mars. That's one we're working really hard on now. The second goal is to dig down under the surface soil to try and find an ice layer. This is an ice layer that was discovered by Odyssey in February of 2002 and has yet to be actually verified that it's truly there. NASA's theme has been follow the water. There isn't any water in the equatorial zone, it's dry. So we thought we'd take them literally and would find a place where there is water, even in the form of ice. But while it's ice today, it may not always have been ice, and we have ways by looking at chemistry and mineralogy to understand the history of that ice.
2 back-to-back NASA Mars missions went awry in the late 1990s. The Mars Climate Orbiter failed, likely due to navigational errors, and the Mars Polar Lander was lost during the challenging entry, descent, and landing phase. These failures led to the next scheduled mission being cancelled. But after considerable introspection, NASA regrouped and in 2005 initiated Scout, a low-budget program guided by the science community. The Phoenix mission is Scout's first attempt.
We took our instruments from Mars Polar Lander and Mars Surveyor 01, and we are using the Mars Surveyor 01 spacecraft. It seemed to us that having that kind of huge amount of heritage was really a big advantage. it gets you far ahead of a blank piece of paper where you're designing a spacecraft from scratch. And so we thought of it as bringing a new bird out of the ashes of the flames that killed the old one, you know, so we called it the Phoenix bird. It's the resurrection symbol.
Unlike the Mars rover mission, which is still driving around near the Martian equator, Phoenix is a fixed site lander and will only be able to sample within 2.5 meters of where it touches down. Fortunately, in 2006, NASA's Mars Reconnaissance Orbiter, or MRO, began circling the red planet. With its high-rise camera, short for High Resolution Imaging Science Experiment, MRO could offer invaluable assistance for selecting both a scientifically interesting and hopefully safe landing site. The principal investigator behind HiRISE is the University of Arizona's Alfred McEwen.
We got there in late northern summer, so the light was fading at the latitude of the Phoenix landing site, so we had to work fast. They did their best to pick the best landing site based on pre-HiRISE data. The hope was that we would just image that location and confirm, yes, this is a good landing site. So we imaged that location and found lots of rocks, boulders that they hadn't known about. And this was in October of last year, so I sent Peter Smith a little Halloween card here, and with the boulders and false colors for Halloween-like colors. But these boulders here, that one is a big one, it's maybe 3 or 4 meters diameter. But any boulder, even some of the smaller ones, 1 meter, they land on top of that. That's the end of the mission. This was definitely a scary sight for them. So then we had sort of a race against time to find a new landing site and characterize it before it got dark at that latitude. We only had really a few months. This went well. We took images at lots of different longitudes. They have a latitude belt where they can land between something like 60 and 72 degrees latitude, which is the right latitude for having ice at the right depth. So we took lots of samples in that band, and they quickly zeroed in on one area that appeared to have fewer rocks. It was a different geologic unit. It was also, ironically, the spot that Peter Smith first wanted to go to when he wrote his proposal was this particular spot. Then they decided that another spot was better, mainly for science in terms of the depth of the ice. But then because of the rocks, that trumps everything. You got to land safely. So then now they're back in that same spot, Region A, they call it. Took those images and characterized that landing site pretty well, and by the end of the last year even, it was pretty clear that they were in good shape. I sent Peter a new card for Happy New Year.
The Phoenix mission to the Martian North Pole is a high-risk endeavor. All previous attempts to land there have failed. But with the launch window looming, the lead scientists at the University of Arizona are hoping to tip the odds in their favor with exhaustive planning and training.
Right now we are about 6 months prior to launch, and we are in the stage where all of our instruments are in their final build and test phase. And the spacecraft is fully built.
Finally, the science team's job is done after 416, and then the sequence team comes in with the spacecraft team and works on taking those inputs from our science team.
We have a system of, at the very top, level 1 requirements and mission success criteria. And those are our project's agreements with NASA headquarters, where we get our funding, of what we have to do and what has to be in place in order for something to launch.
Right now, it's not any good because the camera model's wrong.
If one of the instruments not in that list didn't make it, that wouldn't be considered a mission-ending type of situation.
An assemblage of 7 instruments will conduct the scientific experiments on Phoenix. The robotic arm is the only way to bring samples inboard from the surface to the devices which perform the experiments. The Surface Stereoscopic Imager, the SSI, serves as the eyes of the mission. The chemical character of the soil and ice will be explored by a gas analyzer called TIGA. Another analyzer named MECA will test the composition of the soil and with special needles determine its water and ice content. The rest of the instruments include a camera on the robotic arm, another camera called MARDI, used only during the descent, and a Canadian-made meteorological station, MET. The MET will peer into the atmosphere with a laser called LIDAR.
As far as Phoenix is concerned, the LIDAR will be an upward-pointing instrument able to probe the contents of the atmosphere up to altitudes of 15 or 20 kilometers. I would say virtually all the instruments on Phoenix are all based on tried and true, well-developed terrestrial-based technology in the lab or on field applications in terrestrial applications. But when you take them to put onto a spacecraft, especially one as demanding as going to Mars, then you have to immediately be aware of the mass and the size. You know, to lift this thing and transport it these hundreds of millions of kilometers through the space really does restrict. With Mars, you have a rather small window of a couple of weeks every 2 years and to launch. And if you miss that window, then you're going to have to wait 2 years.
The amount of surface wind will affect how much of a soil sample is blown away as dust and how much dirt remains for the instruments to analyze. In order to gauge the strength of these Martian winds, Phoenix will use a suspended glass tube called a telltale.
It will give us some indications of both wind direction and wind speeds, and it will be imaged, so it will be possible to take an image and show, okay, now that was a strong wind, then and determine what are the correct timing to put samples into the many experiments on board.
With just 160 days of build time left on the mission clock, the science instrument assembly teams are beginning to feel the pressure.
Be back at 10:30.
What's next?
What's next?
The principal investigator is not immune. He's also the principal worrier.
It's going to be very time-intensive because getting the arm to just the right position. From a high-level view, we're in great shape. When you look at some of the details, it's scary.
And now you can click around on the image itself, just
Yeah,
based
but
on
we
the
don't have any
settings, it'll
pictures
show
of that
you
right
an
now.
outline.
We had two major concerns several months ago. One was the landing site selection.
See if there's any rack image of the same target.
There aren't any because this is based on the MIPL data that we had from a while ago.
And the other was the landing radar. If it doesn't work, we don't know if we're near the surface or far from the surface, and if we don't know, we may have to burn so much fuel to be prepared that we may run out of fuel before we get there. We went from a rapid deviation from being on budget, on schedule, technically healthy, everything going smooth, instruments delivered right on time, to a month later, all of a sudden, the schedule's blown, we're out of money, we have technical problems that look insolvable. Where did this come from?
Not trust that unless we had some, some low independent measurements. I mean, I try to get low.
For us, we have another 154 days, I think it is, to find all the problems in the spacecraft and correct them before we launch, and then after that we have no chance to do it. We're building the oven experiment called TIGA, and they had a major setback about 2 weeks ago, and they had to redesign it, rebuild it, requalify it, all in the space of the last 2 weeks.
The frantic reworking of TIGA, Phoenix's gas analyzer, takes place in a dust-proof clean room at the University of Arizona.
Today we're just a week or two away from actually delivering the instrument to Lockheed Martin. We had a problem with the mass spectrometer that we believe we fixed, and we are now testing to make sure that that repair is going to work. TIGA stands for Thermal and Evolved Gas Analyzer, and what it's going to do after we get to Mars is it's going to analyze some soil that we dig up, and it will heat up the soil and see if any gases are given off. And then we actually analyze all of the gases given off from that, from the sample coming out of the oven. We want to understand what has the role of water been in the past history of Mars. And so by looking at the different minerals and seeing how they've reacted with water, we can tell something about the aqueous environment on Mars. And although this mission's not actually designed to look for life, we want to understand the question of habitability and whether the situation is such that ice could exist in the past. For the TIGA instrument, we can analyze 8 samples, and that's all we can do. We're bringing along 8 different ovens, and they can only be used once.
The top goal of the Mars program is to search for life. And the first landed mission to Mars focused very specifically on that, and that was the Viking mission, which flew in 1976. The thing was that the Viking mission found no evidence of organic compounds on Mars. Now, in fact, that turned out to be a significant result because there were less organic compounds found on Mars than one would expect even from an infall from meteorites. So there are less organic compounds on Mars than there are on the Moon. There are all these mechanisms at the surface that would, if there was a record of life, it would wipe it out. So you have to dig to get to that record of life. You have to get into the subsurface. And the question for Phoenix is going to be, can we get deep enough into the subsurface to sample that record?
The first instrument to be installed on the lander is MARDI. It arrives on March the 23rd at Lockheed Martin Space Systems facility outside Denver, Colorado. Delivery of a qualified instrument is a milestone for the instrument team and also marks the beginning of a critical phase for the spacecraft assembly crew.
This one does LiDAR, so we do the card, then LiDAR, and then Mecha has its own logs. So
today, we would be putting 4 instruments on the spacecraft. as you're seeing, we're putting 2 on because one of the instruments is having difficulty in its final testing, and then the order with which we have to build the spacecraft prevents us from putting the other one on. So we're replanning a little bit right now. The biggest challenge really is that when you get down to the last set of electronics that you can build due to the old technology, is you've got no safety net.
So that one is very discolored. Yeah. I wonder if we had to snap a photo of that.
You know, if something goes wrong, if you break those, if something goes wrong, there's very limited spares available. Just because something's worked one time doesn't mean it's going to work again. So we have to be diligent every day, you know, always expecting that there could be a problem out there and making sure we find it when it's there.
It's really an exercise in systems engineering and optimizing the design space. If you push on this here, something else is going to pop up over there. Having a planetary lander is an entirely different endeavor than building an orbiter. It's essentially 2 different vehicles that goes through a metamorphosis in between these 2 primary configurations. The real challenge between the thing is balancing the design needs of a cruise vehicle and a landed vehicle into a single set of design solutions that perform all the functions. So it's really like doing 2 vehicles in one.
And what we have over here, this is what's called the back shell. The back shell is the outer part of the vehicle that protects the lander inside of it during its cruise phase to the planet. It protects it from all the heat and the elements of space. It basically is, it's a one-of-a-kind for this vehicle. There is no other engineering models or qual units or anything like that. It's a one-unit critical item, so if this were to get damaged or something like that, the mission would be over with before we launch.
Most people on the mission believe that, you know, the entry, descent, and landing phase, that 10 minutes when you get to Mars, and you go from 15,000 kilometers per second to, you know, 2.5 meters per second in 10 minutes and transform the spacecraft from this capsulized vehicle down to a lander with legs out. You know, that's just so much to do in such a short period of time with absolutely no margin for error.
Thank you.
Bye. Once we get through that entry, descent, landing, we're safely on the surface. We got 90 days to get things done, and, you know, then time starts running out. You know, I work other lander missions, but I think most people will tell you that we've spent more time on Phoenix testing the surface phase of the mission than most lander programs typically do before launch, because we've got such a short window on the surface to get things done.
We have to do what we call planetary protection essays. So what we do is we verify that we're not delivering any kind of spores or contaminants to the surface of Mars. So what we do is we clean and prep the bottom. Our planetary protection guy comes in and he does the sampling, and then what he does is take it to his lab and he puts it in Petri dishes and he cultivates it for 72 hours to make sure that we don't grow any kind of organisms, molds, so on and so forth.
The engineer's function is to really provide the means for the scientists to be able to carry out their investigations. One cannot exist without the other. Right? Peter Smith is our PI. Peter's a great guy. And the bottom line is we're putting this mission together and we're going to go fly this so Peter and his scientific team can get the science that they're looking for. It's a pretty cool thing. If you're an engineer, it doesn't get any better than building a lander that goes to Mars.
The Phoenix Mars mission is divided into 4 specialist teams. NASA gets the mission off the ground and into space. Lockheed Martin design and build the spacecraft, and will operate it during its journey and throughout its life on Mars. JPL handles navigation and takes over flight operations for the hazardous 7-minute entry, descent, and landing phase. And the University of Arizona is responsible for the science. In all, upwards of 250 people are devoted to this one mission. But for some workers, and even their families, Mars has been a career.
I'm second generation working here for Lockheed. My father had previously worked on the Viking missions. He worked on both 1 and 2 landers there. And like I had said in the past, I worked on the 98 landers, and now I get the opportunity to work on the Phoenix lander. So now I've been building spacecraft here for Lockheed for 27 years.
The human aspect is what makes the whole thing work. We have great computers, we have great technology that help us design and fabricate, but what it comes right down to is the thoroughness and the dedication of the entire team that is really necessary to put one of these things together and to understand the behavior.
The 55-kilogram payload of scientific instruments will eventually be encased in a 40-meter-tall Delta II rocket, weighing in at over 200 tons. This 3-stage missile is designed to propel Phoenix to speeds of 120,000 kilometers an hour toward the Martian atmosphere. Unlike the airbag landings of the Mars rovers, Phoenix is seeking a relatively soft landing. The first one since the Viking missions over 30 years ago. Slowed at first by a parachute, the craft aims to then land only with the aid of 12 thrusters, which must be guided by a sensitive but worryingly temperamental landing radar system.
It's a problem that doesn't seem to have an end to it. We've been working on it for a year now. We've had 3 or 4 different drop tests where we drop this radar out of a helicopter and simulate landing on Mars, and we've found problem after problem after problem. We think we're getting near the end, but this does cause me a lot of worry. Well, just recently we put on all of the instruments in their final configuration, exactly the way they're going to appear on Mars. So it is ready to ship to the launch site where it's going to be integrated into the launch vehicle. We have a couple of months to do the final integrations of the spacecraft to the launch vehicle. We have to put fuel in it. We have to arm the explosive devices that pull things apart as we go through the atmosphere when we finally get there. And so there's a whole series of steps that have to be made, plus a lot of reviews. And finally, it's closing out of paperwork. Paperwork is a major part of a mission of this sort. I think if you took any piece you wanted off an electronics board and pointed to a component or a mechanical piece, you could find a large packet of documentation that goes with that piece. I'd have to say there may be 10 million pieces of paper associated with this mission.
Less than 3 months from launch, the Phoenix lander is completed and must now be airlifted to its launch site in Florida. It's a delicate process. Even a slight jolt to the craft now could jeopardize the entire mission.
Today's going to be one long day. The spacecraft left the Lockheed Martin facility at 4 a.m. our flight manifest calls for liftoff from Buckley Field at 2 p.m. We're going to land at 7:30 p.m. East Coast time, and if everything goes well, we'll have it buttoned up in the clean room at about 11:30 East Coast time tonight. So that's a pretty long day.
Pull out, we'll get into position and then winch in. So probably the safe spot for them would be on the opposite side.
I'm relieved that we're at this point. We've taken this spacecraft apart and put it back together 3 times up until now, and we really didn't start putting it together into this configuration until just about 2 weeks ago. So we put the last science instrument on, I want to say around April 10th, possibly a little bit after that.
It will be a 4,000-kilometer flight from Denver to NASA's Florida launch site. But this is just a short haul in comparison to Phoenix's 680 million-kilometer journey to Mars. After 6 hours in the air, Phoenix touches down on the same runway that the space shuttle uses. The craft is then painstakingly transported to yet another clean room for assessment. This is its last stop until the instrument-rattling forces of the launch, nearly 3 months away. At the Kennedy Space Center, all the pieces of the mission puzzle come together, and the science portion meets the delivery portion of the mission. But before final mating of the rocket and capsule can go ahead, the lander must first undergo a further barrage of tests.
What's next is we will be taking the heat shield off of it, and we'll be lifting off the shipping base and going over to the spin table to do a dry spin and to find the CG and the balance of the spacecraft.
In preparation for the flight and a summer on Mars, the lander and its instruments must go through rigorous testing, including what's called shake and bake. They are encased in a vacuum chamber to simulate the harsh Martian environment, and then shaken vigorously to replicate the forces of launch and landing. The instruments are designed to last for the entire 90 days of the mission, before winter imprisons the lander in thick carbon dioxide ice. Mardi, however, has a much shorter lifespan.
The descent camera is designed to take images as we are descending towards the surface to give us a broad overview of the landing site and also to give us higher resolution views than we can see from orbit. The camera was designed to work and work very well for 2 minutes or 3 minutes, and that was its entire job.
Despite Mardi's modest role in the mission, its memory storage requirements within the craft's onboard computers have created a critical flaw. And during tests at Lockheed Martin, engineers have discovered that Mardi's simple snapshots could lead to a catastrophic systems failure.
We were originally limited to about 20 images, which we would have taken right after parachute descent started, all the way then to power descent and then eventually to the surface. However, a recently discovered problem on the spacecraft has limited us to a single image that we will hope to take somewhere around 300 meters above the surface. There's a computer card inside the spacecraft that my camera connects to, and that card has a problem when it's reading data from the camera at a high rate. It loses track of the number of bytes it's pulling off, and that causes the card to reset.
That same computer card also works with the unit that will make sure Phoenix has the correct attitude during landing. A reset could mean that the craft lands on its head, not its feet. If Phoenix does land safely, the $420 million mission will be headquartered from the Science Operations Center at the University of Arizona. It's the first time NASA will have allowed off-site control of a mission. And in July, a nervous group of scientists meets up to rehearse every conceivable scenario.
Let's start with the most important activity we had yesterday, which was the robotic arm unstow. Matt, are you there were no faults detected. Okay. And did you get an SSI image of its final position? SSI image. Okay.
We are conducting our first operational readiness test, which is our first full-scale test of what we're going to do when we get to Mars.
So there is a set of criteria in your email, Peter?
And working as if we were really on the surface of Mars.
Data you usually do, there's just a particular format to talk to. So look for your email.
Today reminds me very much of almost 10 years ago when we were preparing for Mars Polar Lander. And we were doing these same type of exercises, and they were not going well at all.
Okay, we have a conflict in, we already have a conflict in that
they were very frustrating. Today is a huge advance over what we were able to do 10 years ago.
Aren't we upping the data rate?
Okay, so then this can...
This is a virtual expedition to Mars.
Yes.
As of PM pass. Denise, I told you Flash would be the Achilles heel.
We are running all of our observations on a computer that simulates the spacecraft to a very high degree of accuracy. So when we send commands up to our simulated spacecraft, it reacts just the way the real spacecraft will react.
The spacecraft simulator is based at a mock-up Mars, behind closed doors at the Operations Center in Arizona. Thanks to its fidelity to the real lander, it will be used not only for pre-landing training, but also after touchdown for testing out the robotic commands.
Today, we received data in the morning showing our first pictures of the site in front of the lander where we could dig. And so we went through the process of putting all that data through the system to calculate a three-dimensional terrain model so that we can plan out where to take our robotic arm to scoop up some dirt. And then we, after looking at those pictures, the science team weighed the pros and cons of different spots of where we would dig, worked with the robotic arm team as to what's safe to do, and then from there we baselined a plan to go acquire a sample.
I started back with Viking Lander 1 and Lander 2 in 1976. We didn't have these tools. Everything was done by paper and handing things back and forth. And the process, the interaction with people is very much the same. It's the system end to end, and the system includes people fundamentally, but also the tools and the spacecraft and the whole flow.
Like most complex machines, very few people understand how all the different parts of it work. And so those very few people have to work very hard and long hours between now and landing in order to pull it off. So burnout of the people. But they're a great bunch of folks. If anybody can pull it off, this group can.
When we get closer to actually doing this on Mars, then the pressure of realizing that each day on Mars is costing you $4 million and you don't want to lose one of them, and they're very valuable. It's not just money. The money is just one way to look at value. But the truth is, it's very difficult to get to Mars safely, and once you do, you want to take full advantage of that opportunity, and we will.
With human testing complete, all eyes focus again on the next major milestone, the launch.
We have one more major review before launch, and launch is in, I think it was 16 days to launch. We may not go the first opportunity, so it might be 17, 18, 19, I don't know. But the probability is that we will launch in the first 4 days of our launch window. So right now, the spacecraft is being put onto the third stage of the launch vehicle, and this is happening in a clean room about 10 miles away from the launch pad. And once it's attached to the third stage, then the whole unit, spacecraft plus third stage, is transported over to the launch vehicle and raised up to the top, which is about 13 stories high. On a crane pulls it up and places it on top of the rocket. So I'm a little worried because any accident at this point is unrecoverable. Of course, once we launch, even today, right now, we can't change the hardware. It's done.
Since the 1950s, the controlled explosion of a rocket launch has drawn a crowd to the Florida Cape. The spectacle has become not only a pilgrimage for space scientists, but for the public, the media, and for the families of the engineers who devote years to their art.
This group around here, this is my family that's come down to share the launch with us. When you put so much time and effort into something like a planetary space mission, it's a big part of your life. It's been 4 years since we've been working on Phoenix, and it's really important to me to be able to share it with everybody here.
You don't even know. Every night. We connected the GCB with the XY cord today.
Oh my God.
It was a big step
That's
for
exciting.
Lockheed Martin.
I'm really proud of what he does. I'm really excited for the launch, and really want to see what comes out of this. I think we're looking at good things.
Yeah, I'm interested to see if they find any living organisms in the dirt or soil samples or anything like that. I think that should be interesting.
I hope everything goes right and they find what they're looking for, like water or traces of life.
When we weighed the vehicle after all the things we changed, putting on the full flight configuration, the difference from what we were expecting versus what we measured was 8 grams. So that's less than a quarter ounce difference. After you launch it, there's always a period of discovery when you're learning how your spacecraft that you've worked on for 4 years really behaves when it leaves the nest. As you get closer to landing day on May 25th of next year, and all of the urgency and all the excitement starts to build all over again, it's almost like going through launch again.
Blastoff is scheduled for August the 3rd. But the destiny of the launch itself is out of the hands of the engineers, scientists and technicians, and at the whim of the weather. Lightning during scheduled fueling causes a 24-hour delay. But the team takes the news on this momentous day in its stride.
You know, it's 4 years today that we were accepted on this project, our proposal finally accepted, and here we are, ready to accomplish all the goals we set out in our proposal. We are ready for Mars. I am an optimist. I am extraordinarily confident. I know the team that put together all the pieces of this spacecraft. I know every one of those people, and I am truly confident that they have done a fabulous job, that Phoenix is ready to go to Mars.
Launch of the Phoenix Mars mission is now less than 9 hours away, and the pad is poised for a critical maneuver.
We're in final preparations for what we call the Mobile Service Tower rollback. And this is the structure that surrounds and protects the rocket leading up to launch. Actually pulls back so that the rocket is left on the pad so it can launch into space. If everything goes well, it's about a 30-minute process. It'll pull back about 10 yards and stop to make sure everything's cleared, and it'll pull back all the way. It's kind of like Christmas morning, you know. You think in your mind what it's going to look like when you put the rocket with the boosters, with the spacecraft all together, and it's another thing to see it pulled back and you have this brand new sparkling rocket with this payload that's brand new, ready to go into space and do great things.
This is the culmination of 4 years of hard work. It feels great. I have utmost confidence in our team, in the ULA team that built the launch vehicle, and we are ready to go. We're going to Mars.
We'll launch at about 5:26, so I think about 3 a.m. the last person will be out here, and the closest person at that point will be about 1.2 miles away.
I'm in the control room, along with the rest of my team, and we're doing the countdown, and you know, if anything happens to go wrong, we'll be consulting on what to do. But if everything goes right, I don't have much to do at all. I'm going to run outside the building and watch it actually face-to-face rather than on TV.
Weather is go. SCLC on channel 1 following personnel report ready to proceed with the countdown.
Morning, how are you? How are you? I'm fantastic.
Report ready to proceed with the countdown and remain.
You go up there and you see this whole tower and you don't even see the rocket. It's like this, you know.
Ready. And launch director ready.
5, 4. Main engine start. 2, 1.
Oh, waiting a long time for this. Long time.
17.
How's it feel now? No words. I got no words. It's unbelievable. But I think what's next is a little party.
There you go.
We gotta learn how to run this thing now that it's off the ground. Been spending months and months and months just getting everything working, waving goodbye. But this is going to be a tough thing to run.
Oh, it was fantastic. 4 years of hard work, and we finally see it to go off and head off to Mars. It's just incredible.
Congratulations.
It was great. It was a beautiful light show. I mean, it was everything. The best launch I've ever seen.
It's so fun.
It's too bad Peter's not here, but I know he's celebrating.
I know.
All right.
Another launch, not quite as important. We got to wait about another hour before we know that everything is good, because that's about when we start talking to the spacecraft. But it feels good. It feels great.
Tiga.
Tiga. Tiga. Hey, hey.
Well, you don't see airplane unveils for that.
As dawn breaks, an anxious world awaits news of first contact with the spacecraft. But any fears soon fade.
Well, there's a lot of smiles around this center and around the country today. Pretty exciting morning. Phoenix has left Canaveral Air Force Station. The next stop is Mars.
It's pretty cool. It doesn't get any better than this when you're in this business, to put a spacecraft up and then wait for it to call home and have it respond the way it did. So we're all thrilled.
It's 295 days for our entry, descent, and landing, where we get to do everything that was done today, but we do it in reverse. We go from the velocity we're in now down to 5 miles an hour in 7 minutes. Be a lot of fun. Come see us in JPL on May 25th.
From the position I was in, it was headed directly towards Mars, which was near the Pleiades. The exhaust gases from the solid rockets were still there in a cloud, and the cloud was slowly being pulled by the winds. This cloud turned into what looked like wings and a beak and a long tail, and looked amazingly just like a phoenix bird. The message to me was, the phoenix bird has risen.
Like all the previous journeys into the heavens, the Phoenix bird has risen. It's testament not just to the efforts of this one mission team, but also the dedication of all the scientists and engineers who came before, and on whose triumphs and failures NASA's space exploration program was built. The sentiments of President Lyndon Johnson, praising the successful Mariner mission nearly 50 years ago, ring just as true for Phoenix.
In the history books of tomorrow, unlike the headlines of today, the project's name may be lost, but the names of the men of vision, men of imagination and faith, who made this enterprise such a historic success, is going to be honored in the world for many generations to come.
It's a human endeavor as much as anything. It's not just scientists who care about whether it's a carbonate or a sulfate, or engineers who make sure that resistor is adjusted just right. It's really about the dreams of our population. Everybody is just waiting for that day when the announcement comes that something absolutely incredible has been found on Mars. It changes our whole way of thinking.